For centuries, humanity has dreamed of conquering distance, driven by an insatiable quest for speed. From the first carriages to steam locomotives, then to jet aircraft, each era pushed the boundaries of what was possible, shrinking our world and redefining connection. Today, we stand on the precipice of another such leap, with a vision that promises to make even air travel seem sluggish. But is this revolutionary concept truly ready to transform our daily lives, or does it remain a distant dream? The year 2013 marked a significant turning point with the release of a white paper outlining a concept dubbed Hyperloop. Envisioned as an open-source project, it proposed a radically new form of transport, pods traveling through evacuated tubes at incredible speeds, levitated by magnetic forces. The promise was startling: travel between major cities in a fraction of the time currently required by planes or high-speed rail, all while potentially being more energy efficient. It was a challenge to the status quo, a bold reimagining of how we might navigate our world. At its heart, the Hyperloop relies on two fundamental principles: creating a near-vacuum environment and employing magnetic levitation. By removing most of the air resistance inside the sealed tubes, the pods can achieve far greater speeds with minimal energy expenditure. Magnetic levitation, or maglev, lifts the pod off the track, eliminating friction and allowing for smooth, ultra-fast movement. This combination is designed to propel passengers at velocities that rival commercial aircraft, but on the ground. The theoretical top speed for Hyperloop systems is truly staggering, far surpassing any conventional ground vehicle. Early estimates projected speeds reaching up to 1,200 km per hour, or over 700 miles per hour. To put that into perspective, this would mean crossing the entire state of California, from Los Angeles to San Francisco, in approximately 35 minutes. Such velocity would fundamentally alter our perception of regional travel, turning long-distance journeys into short commutes. Inspired by the open-source ethos, several companies quickly emerged to take up the Hyperloop challenge. Virgin Hyperloop, Hyperloop Transportation Technologies, HTT, and Heart Hyperloop became leading contenders, each developing their own interpretations and technologies. These early pioneers embarked on the formidable task of translating a theoretical concept from a white paper into a tangible, working prototype, attracting significant investment and global attention to their ambitious endeavors. A critical milestone arrived with the construction of DevLoop, Virgin Hyperloop's test track in Nevada. This full-scale, 500-meter-long tube was designed to test the core components of the system in a controlled environment. It was here that engineers pushed the boundaries, experimenting with vacuum conditions, propulsion systems, and levitation technologies. DevLoop represented the first tangible step towards realizing the Hyperloop dream, moving beyond simulations and into real-world experimentation with tangible infrastructure. The most visible sign of progress came in November 2020, when Virgin Hyperloop successfully completed the world's first human test ride. 2 passengers, including Virgin Hyperloop's CTO and Director of Passenger Experience, traveled inside a pod along the DevLoop track. While the achieved speed was a modest 172 km per hour, far from the target, it proved a crucial point: that humans could safely experience travel within a Hyperloop system. It was a monumental achievement, a symbolic triumph demonstrating viability. Despite these successes, the road to commercial readiness is paved with immense engineering challenges. Maintaining a near-perfect vacuum over hundreds or thousands of kilometers of tubing is a Herculean task, susceptible to leaks and environmental factors. Furthermore, ensuring the structural integrity of these vast networks, especially across diverse terrains and seismic zones, requires unprecedented material science and construction techniques. Every kilometer presents a new set of complex problems to solve. One often overlooked challenge is thermal expansion. Long stretches of metal tubing will naturally expand and contract with temperature fluctuations, which can be significant across different climates and seasons. Designing a system that can accommodate these changes without compromising the vacuum seal or structural integrity requires ingenious solutions, from flexible joints to advanced material composites. This isn't just a minor detail, it's a fundamental engineering puzzle for any large-scale pipeline infrastructure. Beyond the hardware, the human element presents its own set of concerns. Traveling at near-supersonic speeds in an enclosed, windowless tube raises questions about passenger comfort and potential claustrophobia. G-forces during acceleration, deceleration, and turns must be carefully managed to avoid discomfort or motion sickness. Engineers are exploring innovative interiors, virtual windows, and smooth ride systems, but creating an enjoyable experience for all passengers is paramount and complex. Safety is, of course, non-negotiable. What happens if there's a power outage, a system malfunction, or even a depressurization event in the vacuum tube? Emergency braking systems, rapid depressurization protocols, and easily accessible escape routes are critical design considerations. The entire system must be fail-safe, capable of protecting hundreds of passengers across potentially vast distances. The lack of an existing regulatory framework for such a system only amplifies these complex safety requirements. Unlike established modes of transport like rail or air, there is no existing regulatory body or set of standards specifically for Hyperloop systems. This means that every aspect, from tube pressure to pod materials, from operational procedures to emergency responses, must be developed from scratch and rigorously tested. Creating these frameworks requires international collaboration and unprecedented foresight, a significant hurdle before commercial operations can even be considered. Perhaps the most daunting challenge is the astronomical cost of construction. Early estimates suggested figures ranging from $20 million to $50 million per mile for infrastructure alone, far exceeding traditional high-speed rail. Building hundreds or thousands of miles of elevated, evacuated tubes across diverse landscapes, tunneling through mountains, and spanning rivers demands massive capital investment. Securing such funding, often from public and private sources, becomes a complex dance of economics and political will. To fully appreciate the financial scale, it's useful to compare Hyperloop's projected costs with existing high-speed rail projects. While high-speed rail is not inexpensive, its established technology and regulatory frameworks allow for more predictable budgeting. Hyperloop, being an entirely new and unproven system, carries significant risk premiums, with potential for cost overruns during R&D and initial construction phases. This uncertainty makes investment decisions exceptionally challenging for governments and private entities alike. Another critical consideration is energy consumption. While the vacuum reduces air resistance, maintaining that vacuum over vast distances, along with powering the magnetic levitation and propulsion systems, demands a substantial amount of electricity. Proponents argue that renewable energy sources could power the system, making it eco-friendly. However, the sheer scale of energy required, especially for a global network, presents a significant infrastructure challenge for energy grids. The design and construction of the pods are crucial for both performance and passenger experience. These vehicles must be incredibly aerodynamic to efficiently move even in a near vacuum, robust enough to withstand potential incidents, and luxurious enough to justify the premium travel experience. Every component, from the pressure vessel to the interior finishes, requires cutting-edge materials and precision engineering, adding to the overall complexity and cost of the system. Unlike point-to-point journeys, a truly transformative Hyperloop system would require an interconnected network, akin to existing rail or highway systems. This vision introduces further complexities: how to switch pods between tubes, how to manage traffic flow, and how to integrate multiple lines without creating bottlenecks. The infrastructure would need to be resilient, redundant, and capable of handling high passenger volumes, all while maintaining the integrity of the vacuum. Beyond the technical and financial hurdles, gaining public trust and acceptance is vital. The idea of traveling in a windowless tube at extreme speeds might evoke apprehension in some. Addressing concerns about safety, comfort, and reliability through transparent testing and clear communication will be paramount. Any major incident, even a minor one, could severely undermine public confidence and set the project back significantly, regardless of its technological prowess. Despite the challenges, the dream of Hyperloop has captured imaginations worldwide. Proposed routes span continents, from the bustling corridors of India to the vast deserts of the Middle East, and across European nations. Each region presents unique geographical, political, and logistical hurdles,
but the promise of rapid connectivity fuels ongoing research and development.
The global ambition underscores the perceived potential for Hyperloop to reshape economies and connect cultures on an unprecedented scale. Dubai, known for its futuristic outlook, has been a strong proponent of Hyperloop technology.
Plans were discussed for a route connecting Dubai and Abu Dhabi, drastically cutting travel time between the two major cities.
While these plans face the same complexities as elsewhere, the commitment from such forward-thinking governments provides crucial support for research and pilot projects.
This showcases how visionary leadership can drive the exploration of new frontiers in transportation.
However, the journey has not been without its setbacks. Virgin Hyperloop, once a front-runner, faced significant restructuring in late 2022, shifting its focus away from passenger travel to primarily cargo applications. This pivot highlighted the immense hurdles and financial pressures of developing such a complex passenger system. While the technology remains promising for goods transport, the pause in passenger development signals a longer timeline for human readiness. The pivot to cargo, while a setback for passenger dreams, underscores a potentially more viable near-term application. Transporting high-value, time-sensitive goods in a Hyperloop system could offer significant advantages over traditional air or road freight.
The reduced G-forces and controlled environment could protect fragile cargo, while the speed ensures rapid delivery.
This strategic shift may allow for continued technological development, gradually paving the way for eventual passenger integration.
Despite Virgin Hyperloop's shift, other companies like HTT and Heart Hyperloop continue to pursue passenger-focused development.
HTT, for instance, has focused on a passive magnetic levitation system, which may reduce energy consumption.
Heart Hyperloop in the Netherlands has developed a test facility with a lane-switching capability, addressing a crucial network challenge. Their ongoing efforts ensure that the passenger Hyperloop dream remains alive, albeit with varying approaches and timelines.
One of the most profound challenges is scaling from short test tracks to continental networks.
A 500-meter test track is vastly different from a 500-kilometer operational line.
Every aspect, vacuum integrity, structural stability, power delivery, and control systems, magnifies in complexity with scale.
This isn't just about building more, it's about innovating new methods for construction, maintenance, and seamless operation over immense distances. The devil is in the details for such a monumental undertaking. Ultimately, the readiness of Hyperloop hinges on a delicate balance of technical feasibility and economic viability. Even if engineers overcome every hurdle, the system must be affordable enough to build, operate, and utilize. Ticket prices must compete with existing modes of transport while generating sufficient revenue to sustain the vast infrastructure. This economic trade-off often dictates the pace of innovation, and for Hyperloop, it's a monumental equation that still seeks a definitive answer. So, is the world's fastest passenger vehicle ready? The answer, unequivocally, is not yet.
While prototypes have been tested and human rides completed, commercial passenger operation is still many years, if not decades, away. The journey from conceptual blueprint to fully integrated, safe, and economically viable transportation network is long and arduous. We have seen significant progress, but the finish line remains distant, requiring continued innovation and immense investment. The development of high-speed rail offers valuable insights. Even with mature technologies, establishing comprehensive networks took decades and vast public investment. Regulatory frameworks, land acquisition, and public acceptance were significant undertakings. Hyperloop faces similar, if not greater, challenges, compounded by its novel technology and lack of precedent. Learning from the painstaking journey of high-speed rail can help temper expectations and inform a more realistic timeline for Hyperloop's deployment. Despite the current hurdles, the vision of a Hyperloop future continues to inspire. The potential benefits, dramatically reduced travel times, decreased congestion, and potentially lower environmental impact, are too compelling to abandon. Even if the timeline extends, the ongoing research and development in vacuum technology, magnetic levitation, and advanced materials will undoubtedly contribute to other areas of engineering and science, pushing the boundaries of what's possible. To bridge the gap from prototype to readiness, breakthroughs are still needed across multiple disciplines. From hyper-efficient vacuum pumps that can operate reliably over hundreds of miles, to advanced sensor networks for real-time monitoring and control, and entirely new materials that can withstand extreme conditions while remaining cost-effective. The integration of artificial intelligence for autonomous operation and predictive maintenance will also be critical for ensuring safety and efficiency. Artificial intelligence is poised to play a transformative role in Hyperloop's eventual operation. AI systems will be crucial for managing complex traffic flows within the network, optimizing energy consumption, and implementing sophisticated predictive maintenance schedules. Crucially, AI will underpin the autonomous control of pods, ensuring safety and precision at extreme speeds, making human error a non-factor in its operational integrity. This intelligent oversight is not just an enhancement, but a necessity. The next phase of testing will likely involve longer tracks, higher speeds, and more complex operational scenarios. Testing lane switches at high velocity, simulating emergency situations, and integrating multiple pods into a coordinated flow will be vital. These future tests will provide crucial data on scalability, reliability, and the overall robustness of the system under real-world conditions, inching closer to the ultimate goal of commercial readiness. Securing sustained investment remains a critical factor. Investors, whether public or private, require confidence in the long-term viability and profitability of such a colossal undertaking. This means clear regulatory pathways, demonstrated safety, and realistic economic projections. The current environment, marked by global economic uncertainties, makes attracting the necessary multi-billion-dollar commitments even more challenging, requiring a compelling and concrete vision for return on investment. From an environmental perspective, Hyperloop promises a potential reduction in carbon emissions compared to air travel, especially if powered by renewable energy. However, the environmental impact of constructing thousands of miles of new infrastructure, including land disruption and resource consumption, must be carefully considered and mitigated. A holistic assessment is crucial to ensure that the pursuit of speed doesn't inadvertently create new ecological burdens. The true green credentials depend on lifecycle analysis. The path forward for Hyperloop is not linear but a complex web of interconnected challenges. It demands sustained international collaboration, massive financial backing, continuous technological innovation, and political will. The journey will be punctuated by breakthroughs and setbacks, as is the nature of truly disruptive innovation. It is a testament to human ingenuity that we continue to chase such ambitious dreams, pushing the boundaries of what was once thought impossible. When, and if, the Hyperloop does become a commercial reality, it will profoundly redefine our world. Distances that once took hours will be reduced to minutes, enabling new economic opportunities, altering urban development, and changing how we live, work, and interact. The world will feel smaller, more connected. The question isn't just whether the vehicle itself is ready, but whether society is ready for the transformative impact it promises to unleash. The dream of the world's fastest passenger vehicle, one that makes our current modes of transport seem archaic, endures. It's a testament to human ambition and our perpetual desire to overcome limitations. While the Hyperloop isn't ready for passengers today, the dedicated engineers, scientists, and visionaries pushing its boundaries ensure that the journey continues. Perhaps one day, the promise of near-supersonic ground travel will be a tangible reality, connecting us in ways we can only begin to imagine.